All right, so we're going to go back to our college algebra days, and we're essentially going to see an application of our complex numbers. Where you guys have probably seen them before is when you're solving a polynomial equation. Essentially, what we have here, right, is we're going to be solving for x. And one way to solve it, and this one's pretty easy, you just kick the 4 over, right, making it negative 4. When you take a square root, as we've seen, we've introduced a plus minus. And of course, this gives us x, and on this side, we end up with plus or minus 2i. So in this case, we end up with a purely complex number, right, which will have some ramifications later on. In the next one, we have a little bit more going on. It's not as easy as just kicking the 2 over because we've got that x. So we basically have to solve this. So one way to solve it is to use our Pythagorean theorem, right? So the Pythagorean theorem basically says that x is negative b, so in this case negative 2, plus or minus the square root of that 2 squared minus 4 times a times c, right? All over 2a, which is 1 in this case. So my solution, right, would end up being negative 2 plus or minus, we have 4 minus 8 all over 2. And so in this case, we end up with a negative 2 plus or minus the square root of negative 4 all over 2. And we already have seen the square root of negative 4, that's negative 2 plus or minus 2i over 2. And so we end up with, there's two fractions here, right? 1 in here, so we end up with negative 1 plus or minus I. So we have two complex solutions right now in the rectangular plane. Okay, so hopefully you remember doing some of this stuff from back in the day. The next one, again, we're solving another quadratic. Rather than doing the quadratic formula, I'm going to remind you guys of completing the square. You could always use the quadratic formula, but I just kind of want you guys to see something that you're going to use in some classes later. So if I'm going to complete the square, right, this part right there represents the incomplete square. So I'm going to subtract 13 from both sides. All right, and to complete the square, I'm going to take the 4, divide it by 2, giving me 2, and then I'm going to square it, giving me 4. So to complete the square, I'm going to add 4 to that. And of course, to keep myself in balance, I have to add 4 to the other side. This side now factors really nicely, as opposed to it didn't factor to begin with. But when I factor it, I get x plus 2 squared, and of course this side over here becomes negative 9. So to solve for x, I'll now take a square root. This will be a plus or minus the square root of 9. This clears out, leaving us with x plus 2, and over here we have plus or minus 3i. So subtracting 2 from both sides, we end up with the solution negative 2 plus or minus 3i. All right, and so basically you can see that complex numbers in an earlier application in college algebra, they popped up when we were solving some quadratic equations, right? So you've seen the square root property, you've seen the the quadratic formula, and then you've seen the completing the square. Those are pretty common ways that we solve quadratic equations. So how in the world does this, apply to later? Well, number one, we've already seen that we can replace these rectangular complex numbers with their polar forms. That's number one. But I'm not going to talk too much about that because that's just a process of redoing it. But in a very, very future application, we're going to be talking about differential equations. And in these differential equation situations, what's going to happen, all right, is we're going to end up solving equations where y is a function that gives us position. So where's my object at? Y prime is going to be known as the derivative, but it basically tells us the speed or the velocity of the object, and y double prime tells us the acceleration. So what I have here in this differential equation is I've got a relationship, I've got an equation that relates my position, y, with the acceleration of that same object. All right, and then same thing here, right? Oops, there's a typo there. That should be a y, and as a matter of fact, there should be a y there. So I have another differential equation that represents my position y with my speed of my object with my acceleration of my object. And same thing here, right? Speed, where am I at? How fast am I going? And how am I accelerating? It turns out that these types of differential equations can be rewritten like the following. And when you take a real close look, right, what I basically have is, in terms of D, I have the same polynomial equations that I had up there in terms of when we're solving for X in a college algebra setting. And so it turns out that when I solve these, we already know the solution, right? In this case, D is plus or minus 2i. Here we got D is -1 plus or minus I. And here D is -2 plus or minus 3i. All right, and to make like I said, there's a connection. Once we change these things to polar, right, what I have is, when I have a differential equation that is purely imaginary, that means that my object is experiencing simple harmonic motion. Or if we were going in the polar plane, it's going around in a circle, right? So it's completing one full circle. So it's not spiraling in and it's not spiraling out, all right? So when you have a differential, if my position, all right, related to the acceleration satisfies an equation like this, I'm in simple harmonic motion, which is why we studied 4.5. In this one, I have a real part and I have an imaginary part. The fact that that's -1 means that my system, right, the fact that I have I puts into play that my sines and cosines, the fact that that's -1 basically means that my function, right, is going to go up and down, but it's slowly going to decay, right? And so if this was a spring mass system, right, this is a spring that's going up and down forever. This is a spring that will basically bounce back and forth and come back to equilibrium. And then I apologize, I actually meant for one of these to be positive. Oh, by the way, what this also means is that if I was a system like this, that means that I'm spiraling in, right? So I'm moving in and I'm basically spiraling to a singularity point if I was in the XY plane in complex numbers. Let me apologize real quick. I just realized that I meant for one of these to have a positive root. So let's just pretend that, how about a matter of fact, I'll make that a minus, right? That we ended up with a positive root there. What this means is this part's telling me I have some up and down motion, and this part means that since it's a +2, that means I'm experiencing exponential growth. So what that means is I've got a wave that basically starts off and it basically gets bigger and bigger and bigger. We call that resonance in some situations. In an XY plane, or excuse me, in a polar plane, that means I've got something that's basically spiraling out as it gets bigger and bigger and bigger, all right? And these kinds of applications happen along an analog to digital circuits. It happens for things that are in motion, spring mass systems, you name it. So that is why we basically study complex numbers. So I wanted to wrap that up because I kind of started this with saying that there's real applications, and then kind of show you what this application will look like in the future. Of course, you got a lot more to build on, right? There's more to say about these polar coordinates that we change to. You have to learn some differential equation knowledge, but I gave you the short version that some of them, not all of them, basically come down to solving polynomial equations, which is really nice. And then depending on the solution, right, that tells me a little bit about how my system's moving in the XY plane or in the polar plane. All right, so that wraps up this chapter. All right, as a matter of fact, I think it's our last official module for the semester in terms of trigonometry, and we're going to be moving to some calculus topics for the remainder of our course. All right, thank you for your time and your effort. I'll talk with you later.